So you're the guy with the helmet. You're basically the driver of a top-notch technology called OpenStack, right? You always want top-notch performance. You always want all the little knobs to configure your system and to configure your environment according to your very complex and specific needs. And obviously, I've been talking a lot to users and to customers. And obviously, there are like thousands of permutations for OpenStack. Everyone can configure each service to his own individual needs and so on. So OpenStack is fairly complex and high-speed moving vehicle. And basically, you're the driver around it, and you're interacting with your steering wheel, which is basically the controller. I'm sure most of you who installed OpenStack basically just had a controller and a bunch of compute nodes controlling those compute nodes, and that would be KVM or Docker or wherever underneath technology for running the actual instances. So the controller is obviously a very important part of your OpenStack. Now, imagine running your OpenStack without your steering wheel. Imagine driving or running your OpenStack environment without the controller, right? Okay, so you can say, my instances keep on running. My instances keep on serving their servers and doing what they're supposed to do. And if the control is down, it doesn't really matter unless I'm a service provider or something like that, and I have customers accessing my APIs. But basically, if something does happen, like how do you control your environment? How do you prevent or how do you fix and bring up those instances back again and keep the environment up and running? So basically, keeping the controller in a highly available setup is extremely important, especially with production environments. But as you mentioned, you've all deployed OpenStack, and you'll know this diagram, and you've seen it quite a lot of times. And this actually emphasizes the point that OpenStack is a very complex beast with lots of permutations, and you have to know every little thing to basically to make the controller highly available. You have to make the keystone highly available. You have to make all the services highly available, Glance, Cinder, and so on. But also you have to take care of the underlying components, right? You have to take care of the database to make sure it runs constantly, and you have to make sure that the message queue in whichever message broker you're using is also set up in a highly available environment. So that's fairly complex. So our engineer sat on that very problem, trying to solve it, trying to build a very good architecture based on our experience with basically providing high availability solutions. Part of Red Hat's portfolio, there's an add-on called High Availability Add-on on top of RHEL, which basically provides lots of components to make services highly available. So our engineers sat on this very problem, trying to solve the HA problem for OpenStack. And the outcome of that was around 6,000 lines of commands you have to type in order to get a fully highly available environment running. Now, one announcement that I would like to make today is basically we're about to release a reference architecture document that actually has everything documented from bare metal to fully running a highly available environment, and that's going to be published in around 2 weeks from now or so. So that's around 6,000 lines of command you have to do manual. That's a very complex task to do, obviously. So today I'm going to talk about the high availability components that we are using in our reference architecture. I'm going to talk about the overall architecture of a highly available environment. And also talk a little bit about different permutation and different layouts that we are supporting today and we will be supporting sometime in the future. So highly available, what does it actually mean? So to most people it would mean making the services available all the time, right? If someone accesses the API, if someone accesses Horizon, the dashboard, you want to make sure he constantly gets his service. If you're a service provider, for you it's extremely critical, but also to drive and to control your environment, that's also important. So the uptime here is crucial, and you want to keep that to maximum as possible. And the second thing is scale, right? If heavy load comes in, you have to make sure that you're able to provide those services through heavy loads. You have lots of instances coming onto running on your environment. You have lots of incoming API requests coming to your OpenStack environment and so on. So you have to make sure that everything not just runs smoothly and everything just runs smoothly when one or two controllers fail, and we all know that does happen from time to time. But we also make sure that everything runs in a huge scale environment. But we also make sure that everything is configured easily, right? That's also extremely important. We don't want to type in 6,000 lines of command every time you provision a new host on an OpenStack environment. Now, there are a bunch of very cool tools to deploy OpenStack and also to deploy OpenStack in a highly available manner. Puppet or Chef are good examples for that you can use basically just to configure the environment. But we want to simplify that whole process of deploying OpenStack, and not just deploying OpenStack, but deploying it in a highly available manner, basically to fit production-grade environment needs. So the second thing I would like to announce today is project we internally in Red Hat call Project Stay Puft. I'm gonna have a talk on Stay Puft during sometime today in a third track. I'm not sure what time it's gonna be. Everything shifted forward. But basically, what Project Stay Puft does for Project Stay Puft is basically a plugin that sits on top of Foreman, and what it does is bring you a nice UI to set up and deploy an OpenStack environment. Now, the key thing for this talk, for the high availability talk, I would like to emphasize is basically we have a little nice radio button saying I want my environment set up in a distributed and highly available manner. And I can choose to deploy it with Neutron or with Nova networking. So basically, I just choose this radio button. This is the layout I'm gonna use. I'm gonna click the next button. Okay, on the controller role, we're gonna have that, and we call it host groups. That's a notion from Foreman. I can just basically allocate hosts to this role or to this host group. So I would just choose 3 or more hosts from my existing nodes that Foreman discovered, and I can basically click deploy. And what Foreman does, it provisions the servers, provisions the bare metal OS, provisions the operating systems on the bare metal, and then runs all the necessary configuration using Puppet underneath to configure the services in a highly available manner. Now, when I say highly available, what exactly do I mean, and how does this architecture, how does it look like, and what do I have underneath? Obviously, as I mentioned before, we have to take care of the database layer. We have to take care of the messaging broker, whether that's Cupid, if you're using Cupid underneath as a message broker, or using RabbitMQ, which are both common technologies for messaging brokers for OpenStack. And in addition to that, I also have to take care of all the OpenStack services, right? I have to take care of Nova, Keystone, and so on, and also I have to take care of Neutron, which is a little bit more complex component, and it's still maturing to be able to be deployed fully in a fully highly available manner. So what components do we use? As I mentioned before, we are using and we are basically shipping all the components needed from the high availability package from RHEL, from Red Hat Enterprise Linux. And the first component that we are using is Pacemaker. So Pacemaker basically lets us construct clustering around the services. Pacemaker basically, what it does is it takes care of the service and makes sure it's constantly running, and it's also constantly running and running smoothly. So if the service goes down, Pacemaker makes sure that the service is rebooted or restarted. And if some failure is still going on in the environment, and Pacemaker is not able to recover or fully recover a service, and the service is not providing the appropriate service it should provide, Pacemaker takes care of that as well, using fancy mechanisms to make sure that the service is not disrupting to the environment. So Pacemaker, as I mentioned before, it takes care of the service. It does monitoring of the service and of the host that runs that service. In addition to that, it also constructs a virtual IP. So each service now has a virtual IP that I can access to, which is basically a single point I can call a service. So for example, I have a Horizon wrapped up with pacemaker and deployed on 2 hosts in this example. So I would just go to this virtual IP, which I also should have a DNS name for, and I go to that host name that's assigned to this virtual IP. And what pacemaker does is basically brings me to one of those hosts. So that's a virtual IP component. We also use HA proxy to load balance the requests. So if I have a huge amount of requests coming to a specific service, what HA proxy does is basically it knows how much load each service has and distributes that request to the least used host to make sure that everything runs smoothly on scale. And those 2 components are taking care of OpenStack services. And those basically are wrapped up. Each and every service we have in the environment is wrapped up in a pacemaker cluster. And each service has its own virtual IP. Now, for the database layer, obviously the database is a little bit more complex. We have to make sure that the data itself is stored in all the hosts, and all the hosts are capable of serving that data. But we also have to make sure that the data is stored consistently, right? There's no way I'm writing one piece of information to one in a database instance, and I'm retrieving another data from another host. So we use Galera for DB replication. So what Galera does is basically it sets up a layer underneath the database services, and what it does is basically makes a multi-master replication across the database nodes. And it's based on its locking mechanism is based on the row locks, so it performs really, really well and relatively small amount of collisions, so it performs really, really well in scale-out environments for the database. And for the message layer, we are using mirrored queues for Rabbit. Fairly common technique in the open source world, where we just replicate the queue from one Rabbit server to the other Rabbit server. So both hosts basically can provide consistent layer of messaging. And on top of that, obviously, we have, as I mentioned before, Pacemaker that has the virtual IP. So that's fairly complex, I think, to explain. Let's go over the diagram and see the flow of the information. Hopefully, this makes the picture a little more clear. So this is me. I'm sitting on the cloud, and I would like to have my Horizon dashboard, right? So I go to this host name or to the IP of my Horizon dashboard, and I get my Horizon dashboard, and I'm happy. Now, this is obviously a single point of failure we would like to take care of. So we have HA proxy in front of 3 Horizon servers that sit on the controller. So HA proxy, now I'm bringing my request to the HA proxy server. And that distributes my request to one of those Horizon hosts. Obviously, all OpenStack services themselves are not storing any information, and they're basically stateless. So this actually allows us to work in this architecture, and allows us to build such an architecture. So my request is distributed by HA proxy to one of the Horizon nodes. But now, HA proxy of its own, it's a single point of failure of its own. And in addition to that, also the Horizon servers are also single points of failure. For example, if one host goes down, I'm remaining with 2 hosts, right? And if another host goes down, then suddenly that host becomes the single point of failure. So what we're doing is basically we're constructing an active-active cluster using Pacemaker around those Horizon Cinder, in our example, as I mentioned, Cinder is basically a stateless service. So it doesn't save any specific information on the server that runs this service, but it goes to the data itself is stored on a centralized backend. So each and every service now, if I have a request coming to any of those hosts, basically this request is served by those servers, and the service itself pulls the data from the centralized storage. Now, Neutron networking layout is a little bit more complex. Unfortunately, I don't have too much time, so I'm going to take the questions in the end. So Neutron is a little bit more complex service. So we do the same as I mentioned before for the Neutron server itself, where we have the pacemaker cluster around the services, we have the virtual IP, and HA proxy distributing the calls. Now, in addition to that, we also have pacemaker clusters around the services that run on the compute nodes, obviously around the Nova and L8 and Layer 2 agents. And all the calls, all the networking flow goes from Neutron server to the compute nodes. Now, we also have a notion with Neutron called network node. Now, unfortunately, network node is a little bit more complex to run in a highly available manner. And the OpenStack open source upstream community is working to enable basically, we have this supported architecture for deploying a highly available OpenStack environment. Now, as I mentioned before, we're soon to ship a reference architecture. In about 2 weeks, we're soon to ship a reference architecture detailing all the little knobs and all the little configurations you have to make in order to run such an environment, in order to build such an environment. We also support deploying this environment using the Foreman OpenStack installer and the project Staypuft. So this uses a pacemaker and HA proxy, and also it uses Galera for the database replication and RabbitMQ for the messaging replication. Now I have some time for questions. Yeah.
Tested the Galera replication under over 3 controllers.
Sorry?
How does the Galera replication handle stress and multiple controllers?
Yeah, so basically the idea behind Galera is to be able to run on several nodes and to manage the locking mechanisms around those nodes. That's what Galera is actually doing. Basically, it's connecting to all the nodes and making a single layer of data store.
So it handles the stress well.
Sorry?
It can handle many controllers, 20 controllers as well.
You can go online and search for Galera statics and how well it handles, but it handles it pretty well in our environment, in our testing, and that's fully supported by us, so we've done all the testing to make sure it handles stress well. But it's also a very, very common, upstream open source technology, so start playing with it because it does handle loads pretty well across multiple nodes.
Single service. What transport protocol you are using?
Sorry?
Single transport. What protocol do you use?
I'm not sure. I can check that.
PGP, ISPAN, how do you...
Oh, backend, Cinder backend. Yeah, so as long as the Cinder backend, as long as all the services can access the Cinder backend, that's exercising, that's NetApp or a Fiber storage, for example, it doesn't really matter. The service itself, the Cinder service itself, is stateless. So as long as the
I understand. Your example was last night. My question is, if I have two single services with the common backend, common spindles, and the single server is stateless, how can the same VM access volume which created in front of one single service by accessing another one? How do you gain high availability of single service with common backend?
So basically what you're asking is how two instances can access a single volume. Is that what you're asking?
No. If I'm creating volume, I'm working in front of single.
Right.
Single creating room and expose the room through PGP, let's say, to the VM, to the host and from host to the VM. Okay? Now the same single box drop down. Say, I have another single volume and I want to access the same volume
Yeah,
through the second single volume service.
I understand. Can you talk to, I'm not sure about the answer right now, I can check that, but I'll have to check that. I'm not sure how it's done on the back end.
What about the availability of the pacemaker?
That's a good question. So basically it could be an endless loop, right?
Yes.
So yeah, you are right. Basically pacemaker itself is also additional service. But the idea of pacemaker is to ship, to enable a highly available environment, right? So
It's a single node distributed?
No. So the pacemaker uses a core sync to sync all the nodes, and each and every node runs an instance of pacemaker. Pacemaker does not run a single node.
So yes,
But on each and every node, it runs pacemaker. Nothing monitors pacemaker itself.
but it designed.
But yeah, we're designing a scale-out way where each and every node of the controllers runs pacemaker.
In concept of network connectivity, the pacemaker, how do you set the state of the application?
So there are several connection states that the pacemaker can say that actually comes more from HA proxy. You can use several states of connection, and HA proxy takes care of that.
No, I mean the connection state is like all the acknowledgement and the states of the network is given by the HA proxy and the pacemaker. But
So yeah, if a node fails, obviously, and you're using a specific node, you have to make all the connections, or the pacemaker has to HA proxy has to take care to switch your connection from one node to another. So that's HTTP state, for example, or that's TCP connection. Depends on the channel.
How do you implement the virtual IP?
Sorry?
How do you implement the virtual IP?
How do I?
Implement the virtual IP.
So pacemaker, that's part of pacemaker. That's what pacemaker does. You have several services, and pacemaker adds a virtual IP in front of it. That's part of pacemaker implementation. That's not something we implemented specifically. That's part of pacemaker enforcing technologies. All right, guys. Thank you. And if you have anything, you're more than welcome to ask questions later.